Auzubillahi minash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Oladimiji T.A., the SS3 physics teacher of CTY Model College, Ibadan. I'm welcoming you to the last class, which is going to be our third class of e-learning class for this week. And in this class today, we want to look at series combination of resistor, inductor, and capacitor. Remember, in our previous classes, we've seen how we can combine any two of resistor, inductor, and capacitor. We've looked at how we can combine inductor and capacitor. We've also looked at how we can combine resistors and capacitor. And lastly, we look at how we can combine resistor and inductor. Today, we want to look at how we can combine all the three. As shown in the diagram, the three are connected in series to an AC source of voltage V and frequency F. You can see the resistor, the capacitor, and the inductor all in series. And when this is done, the opposition to the flow of current in an AC circuit containing all the three in series is known as impedance. Impedance is defined as the opposition to the flow of current in an AC circuit containing a resistor and any one of the three other two, or all the three combined together. From Ohm's law, V is equal to IZ, where Z is the impedance. Working on this, the combined voltage can be given as V square is equal to V square R over plus bracket open V square L minus V square Z, where V is the combined voltage, VR is the voltage across the resistor, VL is the voltage across the inductor, and Vc is the voltage across the capacitor. We can now get V by finding the square root of this expression. But take note, VL comes before Vc because VL is assumed to be greater than Vc. But if Vc is greater than VL, Vc comes before VL, and the formula translates to V is equal to square root V square R plus Vc square minus VL square. Also, the impedance is given by Z is equal to the square root of R square plus SL square minus SC square, where Z is the impedance, R is the resistance, SL is the inductive reactance, and XC is the capacitive reactance. Also take note, SC can come before XL in the formula, depending on which one is greater. We shall look at how we can apply the formulae in solving questions later. Let's move to another subtopic, resonance and power in RLC circuits. That is the resonance and power in an AC circuit containing all the three in series. Resonance occurs in an AC series circuit when the maximum current is obtained from such a circuit. That is, when the current flowing in an AC circuit containing all the three is maximum, then we say the circuit is in resonance. And the frequency at which this resonance occurs is called the resonance frequency F0. And resonance will only take place in an AC circuit containing all the three connected in series when the capacitive inductance, when the capacitive reactance is equal to inductive reactance, that is, when XC is equal to XL. And the frequency at which this occurs is called the resonance frequency F0. To get an expression for the resonance frequency F0, we equate XL to XC because at resonance frequency F0, the inductive reactance is equal to the capacitive reactance, that is, SL is equal to SC. And remember, SL is 2 pi F0 L, while XC is going to be 1 over 2 pi F0 C. Equating the two and make F0 the subject of the formula, we have F0 is equal to 1 over 2 pi square root LC, where L stands for the inductance of the capacitor and C stands for the capacitance of the capacitor. You can remember that omega, our angular velocity, is given as 2 pi f. Then multiply both sides by 2 pi, we can have omega naught is equal to 1 over root LC, where omega naught is known as resonant angular velocity. Now let's look at variation of current and frequency in an RLC circuit. The diagram shown on the screen shows the variation of the current I with the frequency F. As you can see, the maximum current is obtained when the frequency is at resonant frequency, that is at F0. Any frequency below the resonant frequency F0, we have a lower current, and any frequency above the resonant frequency F0, we also have a lower current. We only have the maximum current at the resonant frequency. So from the graph above, it can be seen that at any frequency above or below the resonant frequency F0, the current is less than the maximum current high max. Application of resonance. The resonance circuit finds applications in electronics. It is used to tune radios and TVs into stations. Its great advantage is that it responds strongly to one particular frequency. The other frequencies have very little effect. So hence, such a resonance circuit can select one signal of a definite frequency from a jumble of other signals available to it. That resonance frequency corresponds to that of a particular incoming radio signal. So when this happens, maximum current is obtained and the distant radio station is loudly and clearly heard. Now let's look at examples on how to apply all the formulae in solving questions. Example: an AC voltage of amplitude 2.0 volt and frequency 100 Hz is connected to an RLC series circuit. If the resistance in the circuit is 5 ohms and the inductance and capacitance are 3 millihenry and 0.05 microfarad respectively, calculate the Roman figure 1 inductive reactance, Roman figure 2 capacitive reactance, 3 combined resistance of both capacitor and inductor, 4 impedance, 5 phase angle, and 6 the resonant frequency F0. Solution. From the question we can see that V is equal to 2.0 volts, R is equal to 5 ohms, L is equal to 3 millihenry, C is equal to 0.05 microfarad, and F is equal to 100 Hz. Then to find the inductive reactance XL, the formula is SL is equal to 2 pi FL. Substituting for all the parameters in the formula, we have the inductive reactance XL to be 1.88 ohms. Roman figure 2 capacitive reactance XC, and this is given by the formula 1 over 2 pi FC. Substituting for all the parameters, we have our capacitive reactance to be 31,847.13 ohms. Roman figure 3, the combined reactance X, is given by the difference of capacitive reactance and inductive reactance. Since the capacitive reactance is greater than the inductive reactance, we subtract the inductive reactance from the capacitive reactance, and this gives 31,847.13 minus 1.88, and this gives us 31,845.25 ohms. That is our combined reactance. Roman figure 4, the impedance Z is given by the formula square root R square plus open bracket XC square minus XL square. In the bracket, we are subtracting XL from XC because capacitive reactance is greater than the inductive reactance. And when all these parameters are substituted for, we have the value of our impedance to be 31,847.13 ohms. You can see that there is no change in our impedance and our reactance, our capacitive reactance, because our inductive reactance is so small, so it has little or no effect at all. Then the phase angle is given by the arctan of difference between the capacitive reactance and inductive reactance divided by the resistance. And when all these are substituted for, we have our angle phi between this inductor and capacitor to be 89.99 degree, which is very close to 90 degree. Then our resonant frequency F0 is given by 1/2 pi root LC. Substituting for all these values and solve to obtain your final answer, we have our resonant frequency F0 to be approximately 1.3 times 10 raised to power 7 Hertz. 1.3 times 10 raised to power 7 Hertz. Please pardon the typographic error. There is a power of 7 on that 10 and it is not shown in the note. It is a typographic error. Please put it there. Our resonant frequency is 1.3 times 10 raised to power 7 Hertz. And it is on this note we are going to end our discussion for this week as far as physics e-learning class is concerned. Until next week when I will come up your way again. Once again, my name is Oladimeji T.A., the SS3 physics teacher. And I'm saying, Assalamu alaikum wa rahmatullahi wa barakatuh.